two images, and so this is like about 500 points extracted with a Harris detector, and you can see that, well, there are a bunch of points found, and what's good is that a lot of points, like here on this turret here, is also found on this one there. So one of the things that we're looking for is, remember we talked about reliability, that points that you find on one should be found on the other. But now the question is, given that we found points in two images, image 1, image 2, image A, image B, alpha, bravo, pick your favorite. The question is, how do we match them? How do we determine which points in the left image are the same as points in the right, or multiple images? So to do this, we need what's referred to as a descriptor. A descriptor is a description of the neighborhood where the interest point is, and that's going to allow us to match. Now, we need a couple of properties of the descriptors, and what's important is that these properties sort of trade off. The first is that we want these descriptors to be what we call invariant. That is, they should be almost the same from one image to the next. And so why do I say almost? Wouldn't it be great if they were exactly the same? Well, it would be great if they're exactly the same, but also there were no duplicates. Remember that silly example I gave a couple of lessons back, which maybe you just watched now, or maybe you watched 8 months ago, I have no idea, where I said, you know, if we name everything George, then it's easy to match them, except not really, because everybody matches perfectly, but you don't know which George is the right George. So the way we say that is we also want our descriptors to be distinctive. All right, distinctive means that one point, you know, some particular point here has the same, at the corresponding location, the other image has one descriptor, but a different point would have a different descriptor. And the reason that that's challenging is because these two images are a little bit different, it means even the same point, like the top of that Diet Coke cap that you guys can't see that Megan's been drinking because she drinks a lot of Diet Coke. Anyway, when I move a little bit, the image changes a little. So the neighborhood is not exactly the same anymore. So the descriptor is probably going to change a little bit, but we don't want to change so much that I can't tell that they're the same. But on the other hand, there's another cap nearby that I'd like it not to have the same descriptor so that they can be you know, unambiguously matched. So we have this trade-off between being invariant, found each time, and being distinctive. One is different from the next. So you might say, look, I've got a simple solution.
I've got a simple solution.
We know that the Harris detector gives pretty good detection, and remember we did that whole thing to talk about how to find the right scale, right? So we even know sort of the scale of the window. So why don't we just do this? Why don't we, for every feature we have here, we pick a window whose scale has been determined, and we'll just do correlation against all of the feature points over here using their appropriate scale, and then we just pick the best matches and we go through and do that all the way. That would be a great solution, right? Well, no. If it was, then I wouldn't be standing here telling you all this. So why isn't this so good? Well, first of all, just remembering about correlation, we have these two pictures, and we might have a different picture over here, a camera over here, and the features could have rotated. Right? And correlation is not rotation invariant at all. Remember we talked about how Harris detectors are very robust with respect to the rotation for detection, but to do the matching we have to be robust with respect to rotation as well. Correlation also was pretty sensitive. If I made things brighter or dimmer, etc., I would actually change the values. So remember we introduced this thing called normalized correlation? Well, that's really not your savior either, because it's sensitive to some nonlinear changes, and actually very slight geometric distortions can cause your normalized correlation to get pretty bad. So if as I move and that bottle cap changes its appearance to me just a little bit, the normalized correlation could become problematic. And also this idea that I'm going to take one and I'm going to compare it against all of the others, and then the next one, all of the others, that would be very expensive. So we'd like to do something that's a lot smarter than that. So this lesson and the one next is about sort of essentially overcoming these problems. What I want to talk to you today is about what's called SIFT feature detection. SIFT stands for Scale Invariant Feature Transform. The motivation for the development of the SIFT transform, and this was done by David Lowe back, 99 is really when the community first saw it, and then early 2000s. The Harris operator was not invariant to scale. Now, we've fixed that later, and we talked about how to do scale stuff. And correlation was not invariant to rotation. So what David wanted to do is he wanted to do better matching, and he wanted to develop two things. One was an interest operator, a detector that was invariant to scale and rotation. And we talked about the SIFT detector last time, right? We talked about these finding the maxima of the difference of Gaussians both in scale and in space. And that by doing that you could determine the natural scale, or I should say the right scale. But the other part of SIFT was building a descriptor, that is the description of the neighborhood, that was robust with respect to variations corresponding to viewing conditions. So as you scaled the neighborhood, when you found the right scale, if you changed the brightness a little bit, as you rotated, and those kinds of things, to build a descriptor that would be robust under those transformations. And just inserting opinion here, for these days, for SIFT and things like SIFT, the descriptor is the part that's used most. Okay, that's the part that the idea of building these local descriptors was really significant and continues to be used today. So here's the idea of using SIFT for doing things like alignment or recognition of objects. And the idea is this. You're going to say that your image content, whatever your image is, you're going to transform that into a representation. The word I like to use is a constellation. I'll show you one in a minute. A constellation of local features, and that those feature descriptors will be invariant to translation, rotation, scale, and other sorts of imaging parameters. So if I take the object and I move it over and I get closer to it and I change the lighting, I would get the same descriptors. And so here's an example of shift descriptors. So you see here we've got a truck here, and it might take you a little while to in fact, here I'll show you. These are these little neighborhoods, all right? And these little arrows are just showing you these little neighborhoods. Okay, so we've got ones by the tires and by this thing, and back here by the logo. What might be a little harder for you to see is that we have the same truck right here. All right? And the point here is that a bunch of the same descriptors, so here's one and here's another, they were both found in the two images, right? And if I can find enough matches, then I can figure out, oh, this image has an object, and that object is also in this object. In this image, it's just been rotated, translated a little bit, maybe scaled. And that's the idea about using SIFT for doing the recognition. So if your descriptors were robust with respect to these transformations, you could find them from one image to the next. By the way, here's another description of the problem. This one also comes, I think, directly from the original paper or the second paper. You know, suppose you want to find this box of crisp almond cookies, because we always want to find boxes of crisp almond cookies, in this basket. And what's really interesting about this grocery basket is it has basmati rice, crisp almond cookies, and a computer vision textbook, because when you go to Publix, you always buy a computer vision textbook. Anyway, the idea is, can you find this box that's actually over here? All right? And the picture that's shown in the original paper, which is kind of cool, looks like this. All those cyan lines are the connection between SIFT descriptors found here and SIFT descriptors found here. This is the original image. This is the box located in the basket of groceries. So because it could find all those features, it was able to say, this object is really right over here. This was very impressive at the time. In fact, continues to be sort of a strong way of doing certain types of computer vision recognition. The overall SIFT procedure to recognition was originally defined to have sort of 4 components. The first 2 were finding these extrema, those are those maximums of difference of Gaussians that we looked at, and to detect, localize exactly where they were. So these days, I mentioned this before, a lot of people use the Harris-Laplace method of doing this instead, where you do Laplace in scale and Harris in space. Whatever it is, use some method to find your key points and also to determine the scale of the key points in the image. Then what you have to do, there are 2 more things related to SIFT, and we're going to do them today. The first is we're going to define an orientation. That is, we don't know how the image has been transformed, and of our little local neighborhood, we want to know what the orientation is. And then, once we have an orientation, we can think of that feature with respect to that orientation and build a descriptor. And by the way, I'm using the phrase here, key point. Key point was the terminology used in SIFT. What we're talking about is these detected interest points, and you're going to use them as key points, you're going to use them as features. Key point description is the descriptor we're going to use. All right, here's a picture taken out of, again, the original SIFT work. Here's just a small image of a house on the left. And what this incredibly ugly graphic on the right is just, and we've got better ones in a minute, but this was the original, is just there were all these little key points, and you can see these direction arrows, okay? And those directions are going to be the little local orientation that we're talking about. So let's talk about the orientation assignment, computing the best orientation, okay? Well, that's actually pretty easy. Remember the gradient, and we have different operators for doing the gradients. So what we're going to do is we're going to compute the image gradient at all these points, and then locally we're going to compute some estimate of orientation. And the way we do that is really pretty simple. So nominally, this is your image area with a little line drawing in it, just shown here. But the idea is you're going to build a histogram. Okay, this is our little histogram, where you've cut the angle of orientation into some number of bins. In this particular case, they were using 36 bins of orientation. You know, what's the right number to use is a question. All right? And then what you do is you say, I've got a peak, and I'm going to say, okay, that peak, that's my dominant orientation. And that's going to be the orientation that we use. Okay? Once we've picked that, that becomes essentially our new north. Okay? We're saying that's the way we're going to think about our window here. Now, once we've done that, notice we've found it in XY, so we've removed the translation problem. That is, we know where it is. We found it in scale when we detected the interest point to begin with. We picked the scale, and now we have a new orientation. So what that means is that whatever descriptors we build are going to be invariant to the transformation in X, in Y, in scale, and in orientation, and that's what we wanted.
Here's the dolphin image we've seen before. Let's say our interest point detector found this tip of the fin to be a possible key point. We zoom in on a 5x5 neighborhood around the key point. Now recall how you computed image gradients, say using a 3x3 filter. When we place it over this pixel, what is the dominant orientation you see? Right, it's along the diagonal going towards the top left. Let's use this approach to mark image gradient directions for other pixels. To avoid edge conditions, we only consider locations where the filter fits inside the image patch. Also, we approximate or quantize to 8 directions, vertical, horizontal, and diagonals. Can you figure out the dominant orientation of this patch using the image gradient directions? Select the appropriate radio button. Alright, you might be able to tell just by looking at the arrows. But what's the proper way of doing this? Yes, let's build a histogram. We create 8 bins, one for each possible direction, and then start counting how many go in each. For instance, our first arrow is towards the top left. That goes in here. Okay, how about the next one? Same bin. That's pointing up, and so on. Notice that there is no clear winner. So what do we do? Remember that we need to smooth the gradient histogram. At this level of detail and quantization, each pixel's contribution has a significant effect on the overall histogram. Therefore, we need to soften these contributions, which can be done by smoothing. We see a small bump here, and then a much larger region that wraps around the direction axis. Notice that anything going past the end resumes at the beginning. Okay, now we can locate our peak. It's at the arrow pointing left, and this is our dominant orientation. Pointing left becomes our canonical north, and all the other directions are recomputed relative to it. Our shifted histogram would look something like this. This is the basic idea behind creating rotation invariant feature descriptors.
So now the question is, we need to compute this descriptor about this local image region, all right? And remember, we want two things for a descriptor. We want it to be highly distinctive, that is, given 2 different points in the image, I should come up with 2 different descriptions. But we like it to be invariant as much as possible to small changes in viewpoint, maybe even large changes in viewpoint, illumination, and other kinds of imaging parameters. So before we build that descriptor, we normalize. What's the normalization? Wherever our little window is, we're going to say, okay, this is our new north. We're going to rotate north to be up, let's say. So we're going to rotate them all back. And the other thing is we're going to scale it to be some uniform size. So when we did the detection to begin with, it said it was a small scale, we're going to blow it up to be that size. And if it said it was a large scale, we might shrink it down to be some fixed size. So the idea is that we pick a particular size.